Okay, so let me first give a brief introduction. So it's a great honor and pleasure to introduce our Colloquium speaker, Professor Hiroshi Oguri from Caltech. Professor Oguri has made numerous highly influential research contributions to both high energy theory and the field of mathematical physics. And to list a few of the prominent ones, including his work on two-dimensional both conformal field theories and superconformal field theories, and in particular the relation to Colloquium geometry. And he's also his work on topological string theory, commonly known as BCOE, after the collaborators on this project, and later for his contribution in clarifying the relation between the topological string amplitudes and certain quantity that counts black hole microstates, together known as the OSE conjecture. And he also pointed out some curious unity between geometry and number theory, in the particular case of Matthew M24 group, the so-called moonshine phenomena, that relates this group to some features of the K3 surface. And he has also done many interesting works on ADS-CFT, in particular his joint work with Juan Matacena on strings ADS-3. And lastly, his work, like during the more recent of his works, he has worked on string landscapes and also the swampland conjecture together with Cameron Vapa. And most recently, he has been working on symmetries in quantum field theory, which some of us have heard about yesterday at the seminar. And today he will talk about symmetries in quantum gravity. And Professor Oguri has received his PhD in 1989 under the supervision of Toru Iguchi at the University of Tokyo. And there was an interesting story because, quite amazingly, Professor Oguri was already a tenured faculty in the middle of his PhD at the University of Tokyo. I'm not sure if this has happened anywhere else. But if you know what he has done during the early years of his PhD, maybe you will be less surprised. He has written influential papers on conformal field theories, observable conformal field theories on general Riemann surface, together with his advisor Iguchi. And by the time, shortly before he was defending his thesis, he received another faculty offer from the University of Chicago. Okay, this is before he defended his thesis. He spent several years afterwards. He spent several years at Kyoto University. I don't know why. Maybe Chicago was too cold.
I got married there too.
Yeah,
maybe why.
He spent several years at Kyoto University as an associate faculty, and then joined Berkeley as a full professor in 1994. And he finally moved to Caltech in 2000, where he is the inaugural holder of the Fred Copley Chair. And at Caltech, he's the founding director of the Walter Berg Institute of Theoretical Physics. And he also helped establish the Copley IPMU Institute, the Institute for Physics and Mathematics of the Universe. And he's also currently the chair of the chair of the board for the ESPN of Center of Physics. Professor Oguri has received many awards and honors for his contributions. This includes the Medal of Honor with Purple Ribbon from the Emperor of Japan, the Leonard Essenbard Prize for Mathematics and Physics, the Simmons Investigator Award, the Guggenheim Fellowship, and he's also elected fellow of the American Academy of Arts and Science, and many others. So once again, we are very happy to have Professor Oguri here with us and to tell us about constraints on quantum gravity. Thank you.
Thank you very much for a very generous introduction. I'm on sabbatical this year, so I'm very happy to spend a few weeks to begin my sabbatical year at NYU. The first time to have extended stay in New York, and it's very exciting and having fun, lots of fun discussing with people here. With Eva, I've been discussing every day, and in particular, but with many other people, and so this is my way of introducing myself. So this is one. So I'd like to tell you. So yesterday I gave a technical talk about some of the projects I've been working about symmetry of quantum field theory. But this was sort of more general overview of what I've been doing over the last 5 or so years. And this is about what kind of constraint you can put on low energy prediction of quantum gravity. And So there are a few things I would like to convey to you. One is that we say that the unification of general relativity and quantum mechanics is hard, and that's why we develop quantum superstring theory. But I don't think this has been explained well enough, so I'd like to try to do it again. And then I'd like to explain why string theory is interesting in that context. And I'm going to use the holographic principle as one of the guiding principles to understand the low energy prediction of string quantum field theory. So I'd like to introduce that. And then I'd like to tell you what's known and not known about quantum gravity in that context. Okay, so I'd like to first start out. We say that the unification of general relativity and quantum mechanics is difficult, and so why it is difficult? Well, if you pick some random theorists on this floor or any other floor, then one of the first things you hear is that if you start with this Lagrangian of cosmological constant, Einstein-Hilbert term, and the finite number of matter field, and try to quantize it in 4 dimensions, it's not renormalizable. So you cannot compute quantum gravity effect reliably. Well, this is true statement, but it's not the whole statement. So I'd like to start with that. So for example, there are many other model of quantum field theory for which it's not renormalizable. So a famous example is this pion Lagrangian. And then one of the reasons, the reason that this is not renormalizable is that this has a coupling constant 1 over f squared, and f has a dimension of mass, turned out to be in this case a pion 184 MeV. And then this shows that this Lagrangian is not renormalizable. But even though it's not renormalizable, it's very useful Lagrangian. You can use it to study various quantum mechanical phenomena of pions. As far as you are interested in understanding phenomena whose energy scale is much less than the scale set by this coupling constant, 1f. 1 over f is a coupling constant. Okay? And in fact, you can actually systematically improve the approximation that you can expand things in power of energy of the phenomena divided by f, or momentum divided by f, and expand any physical quantity in power series expansion and calculate each term reliably. And for each term, you can actually do this with finite number of counterterms. And so in this case, even though the theory is not renormalizable, it doesn't prevent us to do some useful quantum calculation.
So what happens if you want to look at phenomena at very high?
So that's where it fails. For example, in this case of pion, you have to discover that it comes from QCD and quarks.
So then
so this Lagrangian doesn't know about it.
Yeah. Okay.
Yeah. So what happens is that beyond this energy, then this Lagrangian is indeed not useful. So this Lagrangian is not the whole story. Mm-hmm. But it tells you some of the story, right. And for energy much less than F, it's very useful. Yeah. So this is a kind of idea that Ken Wilson developed, namely the idea of effective field theory. And in fact, just before this colloquium, I had 1 hour of very interesting meeting with your graduate students. They are very interesting, and we talked about all sorts of things. One of the things we talked about is effective field theory. And so this was developed by Ken Wilson. And so there is this Wilsonian view of effective field theory. For example, the pion Lagrangian we just talked about is a low energy approximation to QCD. And it's derived by performing functional integral while freezing the low energy degree of freedom with pion. And you can in principle derive that Lagrangian in that way, although in practice, you guess that Lagrangian by using symmetry and the known degrees of freedom. And even though that effective field theory is not renormalizable, but you can still make low energy prediction using that theory. And you can say that Einstein gravity is something very similar to that. That even though it's not renormalizable, you can make reliable prediction, including quantum effect, provided that energy and momentum are much less than the cutoff scale, which in this case is called Planck scale. And for example, there are several examples where useful calculation has been done. So for example, there is this Hawking radiation from black hole, and this is a quantum calculation using this Lagrangian. It is not renormalizable, but this is widely accepted to be the property of quantum black hole. And there is a calculation of fluctuation of cosmic microwave background radiation, which I used to infer various things about determining cosmological parameter. And this calculation is again the quantum calculation using Einstein-Hilbert action with finite number of matters. And this is actually my favorite example where you can actually calculate correction to Newton potential. So this is a Newton potential. This one times this is a Newton potential we learned in high school. And then there is a classical relativistic correction to it. And then there is a one loop correction. So one loop correction, you see that there is h bar in here. I recovered h bar. And then this coefficient you can calculate without ambiguity. This happened to be the calculation for the just pure Einstein gravity. So here I'm calculating the diagram like you have two matter fields and you have graviton and then you have one loop and the graviton. And then if you have other fields in it, then here the coefficient can change depending on what kind of matter you have, but these are calculable constants. Technically, the reason is that this coefficient has to do with the log divergence in this calculation. So this is unambiguously calculated. So even though Einstein-Lagrangian is not renormalizable in 4 dimensions, you can do reliable calculation. So but question is that the way Wilsonian approach works may be different in the case of gravity, and that's what is actually the important thing. So the gravity works in a way that is very different from ordinary quantum field theory, in any other fields, in other degrees of freedom we know in low energy. And which is that there is actually a very important mixing of ultraviolet degrees of freedom and infrared degrees of freedom that takes place in the context of gravity, in a way not realized in any other things that we know of. So historically, our sort of progression in understanding physical world from Newton and Galileo 400 years ago is to go to shorter and shorter distance. As we go to shorter and shorter distance, we discover more and more fundamental laws of nature. You go from atoms to nucleus and quarks, and then you uncover more and more fundamental features of the nature. So this is called hierarchical structure of physical world. But it is expected that such hierarchical structure will terminate once we complete quantum gravity. And the reason for one of the reasons for this is the following. Because of this hierarchical nature, we built large accelerator because we think that higher energies that we probe the nature, the shorter distance we probe, and therefore you reveal more and more fundamental feature of our world. And that's why you build a higher and higher energy accelerator. But hypothetically, so let's do some thought experiment. You build the accelerator so big that the collision energy is at the scale at the Planck scale, for example. Then you make black hole at the collision point. And then once you make black hole, as you put more energy into it, black hole grows because in 4 dimensions, the size of the black hole grows as you become more and more energetic, more and more massive. So unlike the energy scale lower than the Planck scale, where as you put more energy, you can see shorter and shorter scale because the momentum is inversely proportional to the length scale. That works differently with quantum gravity or black hole because they are basically, you try to see shorter and shorter distance and you put more and more energy, but then black hole grows and defeats the purpose. So therefore, this is one of the thought experiments, but there are many other reasons to believe that the hierarchy of scale will terminate once we complete quantum gravity. Now, sometimes superstring theory is called what they call ultimate theory or something like that. I don't like the word, but there is a reason that people call it that way. One of the reasons is that at least this historical progression to discover more and more fundamental feature of the world ends once we have the consistent quantum theory of gravity. And that's why sort of we think that the unification of quantum mechanics and general relativity is so one of the ultimate goals that we would like to make progress towards. And So this is what I wrote. The black hole turns high energy into long distance, which is very different from the way that other field theory works. Typically, high energy turns into short distance, but once you have gravity, it works differently. So that seems to suggest that this separation of scale that you need in order to use low energy effective theory idea may also fail with gravity. So, one of the consequences could be that the following: that according to Wilsonian philosophy of low energy effective theory, the idea is that once you identify low energy degrees of freedom and symmetry, then you don't have much more you need to know about physics in higher energy. That you can write down any term in low energy effective action that is consistent, without anomaly, satisfies the expected symmetry and contains expected matter content, and that gives you proper description of the low energy world. So that's the idea of low energy effective theory. But with gravity, with some more subtle connection between ultraviolet and infrared degrees of freedom, this idea may fail. And later, toward the end of my talk, I will present you a few evidences to suggest that there are actually examples where that UV and IR connection exists. And so this is a sort of idea that was sort of named swampland by Kumran Buffer in 2005. That arbitrary low energy effective theory in gravity is not guaranteed to have ultraviolet completion. So this is a very interesting possibility because, yes?
Could you clarify, when people say swampland, what is the swampland?
Swampland is a complement of this set. So,
okay.
So namely that you can consider a set of low energy effective. So I'm going to give you a definition of swampland. So consider a set of all possible low energy effective theory that come from consistent quantum theory of gravity in high energy. So you have this set of low energy effective theory. Now, one might have thought, according to Wilsonian point of view, that you can write down all sort of interaction, all sort of symmetry with arbitrary coefficient in coupling, etc. So that would have been Wilsonian expectation. And but there are reasons to expect that that may not work. That there might be some unexpected constraint in low energy. So that means that there is a set of low energy effective theory that comes from consistent theory, but then there is a complement of it.
Okay.
And the complement of this is sort of called swampland.
Okay.
And that was sort of play on the world landscape. Because landscape is supposed to be the theory that comes from low energy limit of consistent UV theory. And so swampland is supposed to be complement of landscape.
Hiroshi, don't we have constraints on low energy effective theories even when the UV completion is not gravitational? You know, positivity constraints on.
That's right. Yeah. So it's actually, but you can infer that. Yeah, that's right. So this is what precisely we mean by this is we need to clarify. I would like to discuss that. Yes, indeed. So there are subtle constraints in low energy effective action which is not so obvious, even in quantum field theory too. Yes, but before we knew about the anomaly, for the gauge anomaly, we could have overlooked that too. Yes, I agree. But there are more general constraints that sort of non-trivial constraints that are not just covered by this type of condition. So that's what I refer to as the swampland in this case. So that's where I eventually would like to explain. But let me first introduce why the string theory is important in this context. And for that, I would like to introduce the idea of a black hole paradox and the holographic principle. And that started out with the work of Stephen Hawking. So let me briefly tell you what Hawking radiation is. So this is a caricature of black hole. So the horizon of the black hole is often drawn in this 45-degree line because in this diagram, the light propagates in 45 degrees. So once you are inside of the black hole, even if you travel at the speed of light, you cannot go outside of the horizon. That's the definition of the horizon. So outside of the horizon, if you have a quantum field, and the particle particle and antiparticle can be created and annihilated in some finite time scale. But if you have a horizon, one of the particles can go inside of the horizon, and the other particle can escape away. And so in that case, the particle go inside of the black hole can have negative energy. So that means that this particle can have positive energy and escape away. So this was Hawking's calculation of the radiation. And this way you can calculate the temperature of the black hole. And from that you can infer the entropy of the black hole. And one of the surprise was that the entropy of the black hole you calculate using this method turned out to be proportional to the area of the horizon. Yes, you have a question?
Yes, you said that the particle going inside has a negative energy.
Can have energy, negative energy.
Okay, it can have negative energy, but it was created outside.
That's right.
Outside, you cannot have negative energy.
Yes, thank you very much. But you only have finite time to measure it. So for finite time, you have an uncertainty in determining exactly what the energy is. That is why, for example, you can have pair creation of particle and pair annihilation, because you can violate energy conservation with short period of time because you can measure energy precisely. But if you want particle to escape away from black hole sort of indefinite period of time, then this guy has a precise energy. So that means that particle inside of the horizon has to have negative energy. And because time flows in a funny way inside of the black hole, so it can have negative energy. That's the sort of argument. And that's how Hawking calculated this formula. But this is very contrary to what we teach in undergraduate physics, because in undergraduate we teach that entropy is an extensive quantity. So that means that it should be proportional to the volume of the, if this is counting the number of states in black hole, it should be proportional to the volume of the black hole. But it turned out to be proportional to the area of the horizon. So that suggested that the degrees of freedom on the black hole is not in the volume of the black hole, but actually residing on the surface of the black hole. So that led to this idea of holographic principle that fundamental degrees of freedom for region of space-time are defined on the surface surrounding the object. So this is called holographic principle. And it turns out that this principle is realized in string theory, and the way that it is realized is very interesting. So to explain how holographic principle is realized in string theory, I need some preparation. So here is a brief introduction to string theory. So the idea comes from D-branes. So the first start with simple things. So if you have string, so it's a one-dimensional extended object. So it can be either closed or it has boundary, and it has open. So it can be either closed or open. If it is open, then you need to figure out where those endpoint goes. So this endpoint can be anywhere, but it can end on some restricted to end on some surface or curve or point. Okay, so suppose let's consider one of those situations. Suppose it ends on the surface. So then we can consider the following process. So suppose you have closed string propagating from the left, but on this surface, the string can open up and end on this surface, and then recombine and go away. So you can consider such a process if endpoint of string can end on the surface. But you can view this diagram in slightly different way. And if you view it this way, it looks as though the surface is emitting closed string. So this is very interesting because in the context of one of the great things about string theory is that this string, one of these states in this string contains graviton, which exchanges gravitational force. So that's why we believe that string theory contains gravity. So in particular, this means that this surface on which open string can end can emit graviton. So if the surface can emit graviton, that means that this surface is gravitating. So that means that it has mass and energy. So from this we learn that once we allow open string to end on some subspace of the space, then that space starts gravitating. And then if you combine them together, it becomes very heavy and eventually become black hole. And that's how we sort of theoretically make black hole in the context of string theory. But one of the things that we realized was that in this description, the open string ends on the surface of this black object. And this essentially explains why entropy is proportional to the area of the horizon. Because instead of describing this heavy object in terms of closed string, it is now described by open string ending on the surface of the object. And this calculation was done more precisely in certain situations, like by Strominger and Buffer, and then reproduced the black hole entropy correctly. And Juan Maldacena sort of made this more precise by taking certain limit of this construction and led to what is called ADS-CFT correspondence. So this idea you might have heard, so I'll be very brief. But the idea is that you have, suppose you are interested in four-dimensional gravitational physics. Then you cannot, unfortunately, in this technology, we cannot study four-dimensional gravity in asymptotic flat space, but we can study it in the case when the spatial section is hyperbolic space. So we consider the gravitational theory with negative cosmological constant. So the natural classical solution is what's called anti-de Sitter space, whose spatial section is a hyperbolic space. And then in this hyperbolic space, there is an asymptotic infinity, which is a one-dimensional lower space, and on which space you can define conformal field theory, a particular quantum field theory with scale invariance, which does not contain gravity. And the idea of ADS-CFT correspondence is that gravitational theory in this asymptotically anti-de Sitter space is equivalent to conformal field theory at the spatial infinity of the space. And this is supposed to be the exact equivalence of quantum system, which means that any computation you want to do in gravitational theory inside of ADS, you can equivalently do in conformal field theory. So this has had some very interesting application to condensed matter physics. It's a book co-authored by Subir Sachdev, the famous condensed matter physicist, on application of this idea to condensed matter physics. And but in the context of my talk, one of the very interesting development in holography is a deep connection between the structure of space-time and the quantum entanglement. And in fact, it becomes clear that the entanglement in conformal field theory is closely related to how the holography works in a microscopic way. So let me briefly explain how quantum entanglement, or the concept of quantum entanglement. So let me start with a simple case. So suppose you have a two-level system, so two-dimensional Hilbert space of two states, and let's call this Hilbert space HA, and let's make a copy of this called HB, and consider tensor product. So it's a four-dimensional Hilbert space. So there are states with deep entanglement between the two Hilbert spaces, and there are states which has no entanglement. For example, if you consider product of two vectors, one from this Hilbert space and the other from this Hilbert space, there are no entanglement between them, but you can entangle them by considering some superposition of this basis. If you have entanglement, it's useful to have some kind of measure for the entanglement, and one of the measures is called entanglement entropy. So it is defined in the following way. So you take, suppose that you take an arbitrary state. For example, this is called EPR after Einstein, Podolsky, Rosen. So suppose let's take one of those states. And then what you do is that you take partial trace over the second Hilbert space HB to define what's called the entanglement density matrix. And you calculate the von Neumann entropy for this density matrix. And this is a good entanglement measure. So for example, if you use this state with no entanglement, this entanglement entropy is 0. And if you use a EPR pair, this entanglement entropy becomes 1. So this is a useful measure for the entanglement. And more generally, you can think of, if you choose arbitrary state, the entanglement entropy can be thought of as something like roughly the number of EPR pair of the state. So in the following sense, that suppose you choose a particular state, and you take any tensor product of the same state. And if you calculate the entanglement entropy, then this roughly tells you how many EPR pair you have. So this tells you this is how this is a good measure for entanglement entropy. So after ADS-CFT correspondence, correspondence was proposed about 7 or 8 years after the proposal, some people, especially condensed matter physicists and working on this kind of program, wondered how you can actually do this kind of calculation in the context of ADS-CFT correspondence. And they come up with the following kind of situation. So ADS-CFT correspondence says that anything that is happening inside of the untilted space, so anywhere on this surface, can be understood by considering Hilbert space of the conformal field theory on the boundary. So this is the boundary. And now suppose you separate the boundary into 2 segments, one region and its complement. And then roughly speaking, there is a Hilbert space associated to A, and then there is a subspace of the Hilbert space associated to A bar. So roughly speaking, the total Hilbert space is a tensor product of this. If you are mathematically rigorous, there is what's called Tomita-Takesaki theory, which gives you more precise way of stating it. But roughly speaking, the situation is very similar to here, where you have a Hilbert space over some region A and the Hilbert space over some region B. And then you can ask, well, suppose you have a vacuum state of the whole system, how do you calculate the entanglement between A and its complement? And this collaboration between condensed matter physicist Shinsei Ryu, who is now a faculty at Princeton, and Tadashi Takayanagi, he's a string theorist at Kyoto. So I guess my understanding is that Shinsei asked Tadashi, well, how would you compute entanglement and entropy like that? And then they discussed over dinner, and they came up with the following prescription. That is, suppose you have this region A, the natural thing to consider is that where A have a boundary, so you consider some kind of minimum surface inside of the untilted space, which is subtended by the boundary of A. Okay, so this is this red curve. So you measure the area of this red curve and divide by 4 Newton. When they wrote this formula, they didn't have any good argument. They just speculated based on the similarity with the Bekenstein-Hawking entropy formula, which is to divide the area of the horizon by 4 times G Newton. So they use a similar, they are sort of inspired, and they thought that, well, maybe similar formula works because it's called entropy. So they suggested that the entanglement entropy for this region should be given by area of minimum surface subtending this region. Turned out to be true. So it was actually proven very soon, and in fact in their paper, that it works in 2-dimensional conformal field theory. And then it was later shown by Arnold Senner and his collaborator in a more general setup. So I meant to actually discuss some interesting feature of this entanglement entropy, but given the time, I would skip it. And
excuse me, can I just ask a simple question?
Sure.
Why is it that the gravitational constant enters into that formula? If it's for, I get it why it should be in the.
Yeah. So it's a good question. So there is actually some kind of dictionary between quantity in gravity and quantity in the conformal field theory, because this is a relation between gravitational theory and conformal field theory. So you have to translate every quantity you calculate in the gravitational side to the calculation in conformal field theory. So for example, one of the quantity is that in the gravitational theory, you have a Newton constant. You also have untilted space. That means that you have the curvature radius of this hyperbolic space. And so you have to interpret those numbers in the language of conformal field theory. So I give you one example. So in conformal field theory, in any quantum field theory, you have energy momentum tensor. So you can write down energy momentum tensor. And then you have another energy momentum tensor at some other point, W. And so suppose you calculate 2 points. Okay. And so energy momentum tensor has a dimension D in D dimension. So that means that 2-point function would have like dx minus W of D, 2D, I think. And then there is some kind of coefficient. This coefficient is interesting to calculate. this coefficient, this is a totally quantum field theory calculation. This coefficient turned out to be in the gravitational side is related to the curvature radius. Measured by Planck length to some power, which I forgot. It depends on the dimension. So Planck length is of course related to Newton constant. I think the Newton constant, 1 of the g Newton, is like Planck constant, Planck length. So let me try to remember. So it's a Planck length to the d. In this, if this is d, it's d plus d minus 1, I think. So this is like that, and so this translates. There is a dictionary between the Newton constant measured in the unit of curvature radius of unitary space to the 2-point function of energy momentum tensor. There are some tensor structure. I didn't write it.
G Newton, not 1 over G Newton.
Yes, that's right. Yeah, so that's 1 over G Newton. Thank you very much. Yes, thank you. So there is some relation like that. Okay. So yeah. So I assume that we're gonna do this translation to relate. So this is the expression that you can calculate in the gravitational side, and if you use that kind of dictionary to translate that in the CFT language, then you get the right formula. That was what they proposed. Okay, so this leads to some sort of refined version of holographic principle, which was actually, so after Ryu and Takayanagi proposed this correspondence, many people worked on it, and then they realized that there is actually a refined version of holographic principle. The holographic principle says that anything that is happening in this uncertain space here can be understood on the boundary region. But there is actually a refined version of this statement that says that suppose you have this region A of the boundary, and then consider this Ryu Takayanagi surface. Then there is a shaded region. Then anything that is happening in the shaded region can be encoded in this subspace A. So there is this kind of refined version of correspondence. So this sounds like a very innocuous statement, but that led to a puzzle, and that resolution of that puzzle uncovers that the way that the holographic principle works is very closely tied to how the quantum error correcting code works in quantum information theory. So I'd like to explain that. So let me make a couple of transparency to the slide page to explain it. So there is actually a puzzle. There are actually two puzzles. So let me explain this side of the puzzle. So suppose this refined version of the correspondence says that anything that's happening in a shaded region can be encoded in the subspace of the boundary quantum theory. Okay? So suppose this is true, then let's consider something that is happening inside of this uncertain space, some event, some bomb explode or something like that. Now suppose you divide the boundary region into 4 segments, and then if you pay attention to this segment, that segment knows about this shaded region. This segment knows about this shaded region. This segment knows about this region. This segment knows about this region. But even if you combine all the information, none of that tells you about what's happening in the middle. Okay? So that's very puzzling, because in ordinary quantum field theory, we thought that the informations are local, because it's a local quantum field theory. So if you consider something happening locally in this region, this region, this region, this region, then we should be able to recover everything about what's happening. But this is a counterexample that holographic principle should have thought. I should have thought that I know what's happening here, but you cannot reconstruct it from here. That's a puzzle. Another puzzle is that suppose you can have this overlapping region, and the same event can be encoded in this region or this region, and so that means that the event does not have a unique presentation. So how do I think about it? So it turns out that there is actually, as I advertised earlier, there is a deep connection of this mechanism to quantum error correcting code. So quantum error correcting code is an idea that was developed in 1990s by quantum information theorists to protect quantum information. So in ordinary classical quantum computer, the classical computer like the one that I have over here, you want to protect the information from error. That very often the thermal fluctuation or error in tips misplace information. And the way that the basic idea of how to recover the information is to make redundancy. So you make multiple copies of the same data and then check, and then majority vote determine which information is correct. So that's the sort of idea of classical error correcting code. But that does not work in quantum computers. The reason is that there is this thing called the quantum no Xerox principle. That is that there is no unitary transformation between from a state in the Hilbert space to a copy of the same state in the tensor product Hilbert space. So that means that you cannot just sort of straightforwardly make redundancy by making multiple copy of the same state and then take tensor product, because there is no unitary transformation which does that. So instead, the way that people come up with that is that you make a big Hilbert space, which is a tensor product of the same Hilbert space, but take a particular subspace of that Hilbert space, which goes in some sense diagonally in this tensor product Hilbert space, which has lots of entanglement between different Hilbert spaces. And basically, you encode the information in this, encode the information in the entanglement between different Hilbert spaces. And so if you do that, even if you lose the information about a particular factor in the Hilbert space, you can recover it by knowing the type of entanglement. So that's sort of the idea of quantum error correcting code. And so if you think about that, in fact, this is exactly what happens in the holography, because what happens is that you cannot recover the information about this point by knowing the information about here or here. But if you combine information from here and here and here together, this covers this entire region. So that means that the information about what's happening in gravitational theory deep in the inside of anti-theta space is encoded in the entanglement of the quantum system around the boundary. So that's sort of the idea. Okay. So that's sort of rough abstract tour of holographic principle in quantum gravity, and I'm going to use that to derive some of the low energy prediction of gravitational theory. So that has been a preparation for the rest of my talk. I hope I still have 15 minutes or so to make presentation on that. And so as I'd like to apply this, and so coming back to the swampland question. So the swampland question was the following question: that given an effective theory, how can one judge whether it is realized as low energy approximation to consistent quantum theory with ultraviolet completion, such as string theory? It doesn't have to be string theory, but it has to be consistent quantum gravity. And if you have that, how can you determine? So it's delineate between landscape and swampland. So that's the sort of swampland question. So this was posed by Qumran Buffer, and I gave one of the first non-trivial example of this swampland criterion. So in particular, constraint on symmetry has been a very interesting thing about physics. And in fact, yesterday I talked about symmetry in quantum field theory in the technical talk. So it has been useful in identifying formulating fundamental laws of nature. And also in condensed matter physics, it has been useful to predict the dynamics and the phases of matter. But symmetry is also rather deceiving, because, for example, gauge symmetry in quantum field theory is not a well-defined concept. We now know that there are lots of examples of quantum field theory, notably what's called Zeiberg duality, where the gauge symmetry and the matter contents are not unique. That there can be multiple low energy effective theory description with different gauge symmetry, which gives you the same quantum field theory. So on the other hand, global symmetry seems to be well-defined concept because it's acting non-trivially on the Hilbert space, and so its action is well-defined. So it's independent of which Lagrangian you use. But I would like to argue that consistent quantum theory of gravity does not have such thing, the global symmetry. So that means that gauge symmetry is ill-defined, and the global symmetry does not exist in the end in quantum gravity. So there is a standard argument of why quantum gravity cannot have global symmetry, and so this is why people long believed that quantum gravity cannot have global symmetry. So this is based on the idea that black hole can emit Hawking radiation, like I discussed earlier. And in that case, you can actually have some a series of arguments that says that this leads to some kind of inconsistency. In fact, at the graduate student meeting just before this colloquium, I gave you a detailed explanation of how this works out. But in view of time, I probably would like not to spend time on this because I will give you a better proof. There's a loophole in this argument, and so I wanted to give an airtight argument for this. So what I did with Daniel Harrow 5 years ago was that we formulated this absence of global symmetry conjecture in a precise way in the context of ADS-CFT correspondence. Of course, ideally, we would like to prove the absence of global symmetry in our universe. So in the asymptotically flat gravitational theory, but we don't have a mathematical definition of this. And so if we don't have mathematical definition, I cannot prove rigorous theorem. So we try to do the second best thing, which is that to look at the gravitational theory, of which we have a definition, which in terms of ADS-CFT, and in that context, we actually give a rigorous proof of why such theory cannot have global symmetry. So the idea is a Noether theorem. Noether theorem says that if you have symmetry, then there is a conserved charge. And if you have a continuous symmetry in particular, then you have a Noether current, which is conserved. So this is called Noether current. And then unitary operator that implement the symmetry can be expressed as integral of zeroth component of Noether current over spatial surface, and then some coefficients, Q, I, or something like that. So this is a Noether theorem. So this operator implements a symmetry on the Hilbert space. So one of the things that Noether theorem does is that if this sigma is a union of some disjoint subspaces, since this is an exponential of integral, you can write this sigma into product of unitary operator acting on each individual subspace. It turns out that so you can easily prove this for in the case of a continuous symmetry, but it turns out that this is true even for discrete symmetry. This statement that if you divide a subspace into product, then this unitary operator becomes product. Okay, so this is actually this is called the generalized Noether theorem. This is a theorem that you can actually prove rigorously using the language of algebraic quantum field theory. Okay, so if you use that and combine with this idea that holography works just like the quantum error correcting code, we can prove that quantum gravity cannot have global symmetry. So here is a one-page proof. So the reason that I have had the long tour of entanglement was to show that this theorem can be proved in one page. And so the idea, suppose to the contrary, that gravitational theory in anti-theta space had global symmetry G. I would like to present a contradiction. If there is global symmetry, there must be some local operator which transforms faithfully into another operator at the same point, because otherwise we cannot call that a symmetry. If the symmetry acts trivially on every state, then it's not a symmetry. So there ought to be some operator. But that leads to a contradiction, because suppose I place this operator somewhere in the middle of anti-theta space. And suppose you divide the boundary into segment, and then the unitary operator acting on it, we should have Noether theorem, so we should be able to write it as a product of operator acting only on the individual regions. But then operator acting on this region 2 can also only affect what's happening in this shaded region. And the operator acting on this region 3 can only affect the phenomena on this shaded region. So that means that this operator U of G, written in this way, commute with this any local operator in the middle. That's a contradiction because we assume that there's a global symmetry in uncertain space, and therefore there must be a local operator here that has non-trivial commutation with this unitary operator. But I just proved for you that because of Noether's theorem, that cannot happen. So that's a contradiction. Okay? So that's a one-page proof that the quantum gravity cannot have global symmetry. Okay, so this is something that I can prove rigorously. But there are other things that we think are true, but we don't have a rigorous derivation of this conjecture. There are various circumstantial evidences, and some are very solid, and some are very shaky. Do you know who is this guy? This is Paul Ginsburg, that I think everybody is benefited by him. And this is taken near the Aspen Center for Physics. And I like this picture because we are having work and he went in this direction and it just happened to be right next to it. It looks like actually he represents his attitude towards his life. But this is the direction we are going in the next 10 minutes or so. So by now, there are actually several speculations about the property of low energy effective theory. Some are very well established, and in fact, in the case of absence of global symmetry and completeness, which I haven't told you about, have some rigorous proof, at least in the case when you can define what quantum gravity is in the context of anti-tensor space. And then there are more speculative conjecture, which turned out to be more useful. So this is a diagram I often draw. So in the horizontal axis, you have usefulness and uselessness. And then there is a rigorous and speculative. And just like everything else in life, it stays on the diagonal line. And then basically one of the things that I'm attempted to do is to move this diagonal towards this corner, where it's both useful and rigorous. And so that's what basically I'm trying to do. And I'll give you a few examples of this conjecture on this diagram. So let me start from this line. So there is this thing called weak gravity conjecture. So this is the idea that gravity is the weakest force in nature, which of course we are very familiar with. For example, this cartoon demonstrates that the magnetic attraction is stronger than gravitational attraction. So, I told you about absence of global symmetry. So that means that if you happen to have global symmetry accidentally in low energy effective theory, for example, the standard model of particle physics has baryon minus lepton number symmetry, which is an accidental symmetry. If you try to write down low energy effective action with the particle content of standard model and symmetry, then inevitably B minus L is preserved. But we believe that if you take into account some ultraviolet effect, such as grand unification, the V minus L would be violated. But this quantifies that. This explains that the gravitational theory should not allow such symmetry, but it doesn't tell you how it is broken. And it will be useful to know how global symmetry is broken, because if you know how baryon number is broken, then I can tell my colleague at Hyper Kamiokande how big their water tank should be. So that would be a very useful knowledge. So weak gravity conjecture in some sense quantifies it. So this is a conjecture that's formulated by Al-Kani Hamed and collaborator, that it says that if you have any low energy effective theory described by Einstein gravity coupled to Maxwell field and finite number of matter, and if it has an ultraviolet completion as a consistent quantum theory, then the theory must contain the particle of charge Q and the mass such that this inequality holds. So this is the conjecture. And so this is motivated by black hole physics, and just very similar to the argument that I gave about absence of global symmetry. And all known construction, top-down construction from string theory satisfies this inequality. And there are also very intriguing connections to cosmic censorship hypothesis. And one of the things I've been trying to do for the last 5 years or so is to give you a rigorous derivation of this in the context of ADS CFT correspondence, which we haven't been able to do it But instead, what I have succeeded in doing it is to derive some interesting consequence of this. So I only have 5 more minutes, so maybe I'll just flash the inequality. So here I give you some argument. And then one of the things I wanted to do was to show that your colleague Sergei Dubovsky has done some interesting idea work that which I'm going to use. But Sergei just realized this morning that he has flight to take to somewhere. So now I don't have to explain this maybe. But anyway, so he has a very interesting paper with Nimar Hamed and collaborator that says that, well, we have a standard model of particle physics, which we believe is correct low energy effective theory. We have Einstein gravity. So that means that that theory should not be in swampland, right? So we have this consistent theory. Otherwise, we assume we are living in mathematically consistent universe. So suppose this is given, and suppose you consider such a low energy theory and put it on consider compactifying on one of the circle, and then reduce the theory in low dimension. Then you get some kind of low energy physics. And then Cameron Buffer and I looked at this and thought it was very interesting, and combined their observation with weak gravity conjecture, and came up with a very curious inequality that the mass of neutrino raised to the power of 4th in the standard model has to be bounded from above by the dark energy density. They have the same dimension. But it turns out that this actually is very actually close to what we observe. So this is a more precise version of this inequality. So lambda is the density of the dark energy of our universe. So there are several neutrinos. So I'm having some of our neutrinos mass raised to the power of 2 or 4. And then there are some coefficients which depends on whether neutrinos are Majorana or Dirac. And then, so basically this is an inequality that can be inferred from the weak gravity conjecture and the argument by Sergei Dubovsky and his collaborator. And this is actually very close to be excluded, but not quite excluded by the current experiment. And so this is very interesting. So many people observed that there is actually a very close connection between the scale for neutrino mass and the scale of dark energy of the universe. But weak gravity conjecture can potentially explain the why they are so close, because there is such a relation. And so you can think of this in 2 different ways. One is that this gives you lower bound for dark energy. And so this is an interesting thing. And another way to think about it is that if you know the dark energy of the universe, then it gives you upper bound for neutrino mass. And so this is a this can be a principle that is alternate to naturalness. So naturalness has been a dominant paradigm in particle physics for over 4 decades. That people believe that naturalness should guide us to understand, to predict physics beyond the standard model of particle physics. But then LHC at CERN didn't discover supersymmetric particle, and that has cast some doubt about the usefulness of the naturalness as a guiding principle. This can give you an alternative paradigm to explain why neutrinos are light. So this is potentially interesting. So there is actually another interesting conjecture called the distance conjecture, which I'm going to explain in the next 1 minute. And one of the consequences of this conjecture is that it gives you upper bound on the cosmological constant. So this gives you lower bound, but this also gives you upper bound. And this is an interesting, because if the distance conjecture is true, then this gives you, in principle, derivation of why dark energy of the universe is so low. And this does not use anthropic principle. So this is making this more rigorous is also a very interesting direction to go. So this motivates me to explain in the next 30 seconds this line of research, and this called distance conjecture. And so this is motivated by, one of the motivations is following. So suppose there is, so I told you that there is no global symmetry in quantum gravity. And in fact, the proof that I derived with Daniel Harrow works also for spontaneously broken global symmetry. But if the global symmetry is spontaneously broken, there is a Nambu-Golson boson, so there is a flat direction in potential. But my proof with Daniel shows that even that should be broken. So that means that there must be actually the Goldstone, the potential for Goldstone cannot be totally flat, that it has to terminate somewhere. A distance conjecture sort of quantifies. So distance conjecture comes from the idea that the theory of quantum gravity cannot have free parameters, that all the parameters should be explainable. And so in fact, this idea originates from Albert Einstein. So this is an autobiographical note of Albert Einstein. And in this note, in this passage, he explained the notion of natural unit. It's actually, he explains the natural unit in a beautiful way. And he says that if you express all the laws of nature in natural unit, then everything is expressed by fundamental constant. But he believes that there is no such arbitrary constant of this kind. And only rationally, that is to say that nature is so constituted that it is possible logically to lay down such strongly determined laws that within the law, only rationally completely determined constant occur. Okay? So distance conjecture in some sense is sort of a more modern formulation of this Einstein's belief. And unfortunately, I do not have time to explain what the distance conjecture is, but basically it is a conjecture about the range of scalar field expectation value in the low energy effective theory. And if you have that conjecture, if you have such conjecture, then there are a variety of predictions you can make. So for example, in the model of early universe, there is a thing called the inflation model, which postulates that there is actually, in low energy effective theory, there is a scalar field whose potential is very flat in a very long range of the scalar field expectation value. And that this distance conjecture that Kamran Baffa and I formulated give you upper bound for the range of scalar field, the range that scalar field travels in the unit of Planck constant and Hubble scale. So this gives you upper bound, and so this is very interesting. So here is for example one of the predictions. So if you have inflation can generate primordial gravitational wave, and that can be encoded in the tensor scalar ratio, which is often denoted by R, of the B-mode polarization of CMB. And so this is plotted in the horizontal axis. R is a tensor scalar ratio of B-mode polarization of CMB. And so that requires, so what's called the least bound, give you upper bound for the range of the scalar field potential travels in order to realize this R value. But this potential, this gives you, they give you lower bound, excuse me. So namely that the least bound says that in order to realize large value of R, the scalar field has to have large range of variation. On the other hand, the distance conjecture gives you upper bound for the range of the potential. So that means that when it intersects, over here, you cannot have actually consistent inflation model consistently with the distance conjecture. So there is actually an interesting story that I just wanted to tell, which is that when the bicep discovered thought that it detected the primordial B-mode polarization, about a month ago, the dean of our Caltech department heard about it because Caltech was involved in the bicep. So I was at the deputy dean at the time. So I was actually doing some administrative work in my office, and the dean came in and they said that, you know what, I know what R is. 0.2. So my first reaction was that great, it kills string theory. I should have put it in writing, but I think I can prove this because he teased me very often afterward. But there's a reason that I said that, because if it was 0.2, it would have contradicted with my conjecture and with lifespan. So anyway, so this is very interesting because potentially, I mean, I think Planck is now over here and it can go down here in next 5 years or so with new experiments. So it'd be very interesting to actually sharpen this conjecture to see whether these exclude or allows this type of set. I wanted to tell you about Dojita conjecture also, but maybe I'll skip that. It will also give you some interesting prediction about B-mode polarization. So I think that this distance conjecture and Dojita conjecture, they do not totally exclude inflation model, but gives you very strong constraint on these models. So I think it's very interesting to sharpen this conjecture and put them in a more rigorous footing. So I have been the director of Institute for the Physics and Mathematics of the Universe at the University of Tokyo. One of the things we are doing is to launch a satellite towards the end of this decade to measure B-mode polarization. So one of the tasks I would like to do is to make this more precise so that we can compare this with this experiment. And yeah, so this is the range that, so it can potentially go to 0.01 or even lower. So that would be very interesting. So by now, we have this kind of web of swampland condition, and these are very closely tied to various interesting observable phenomena. So the way I think about it is this program of swampland is some kind of conduit from formal development in string theory to testable prediction. So over the last 3 decades or so, string theory have been developed. And we learned quite a bit about the formal aspects of quantum gravity, such as black hole, quantum field theory, or geometry and string theory, etc. And so we have like vast knowledge on this. And then swampland program can potentially utilize this, leverage that, and then to make some useful statement about cosmology and particle physics. So I think that's an interesting program to explore. So, in the end, the message I wanted to tell you is that gravity is very different from other quantum field theory. That unlike other quantum field theory, mathematical consistency at high energy imposes very strong constraint on effective theory. So Planck scale is very far away. We cannot build the accelerator to directly probe that. But we may find some surprising prediction on low energy by thinking about this program harder. So thank you. That's all I wanted to say. I apologize, I went a little bit over time.
Questions?
He's raising hand.
In the global in the symmetry conjecture, in the no global symmetry, you have a local operator that sits at the center. Now, doesn't gravitational dressing tell you that there
Right.
must be a
So to be precise, there is no exact local operator in quantum gravity because of the diffeomorphism invariance, but you can do gravitational dressing. And what it does is that give you a little bit of size to this one, but that does not, that is fine because we can make this decomposition of the boundary into smaller and smaller segments so that we can actually reduce the overlap between this quasi-localized operator and the boundary region smaller and smaller. So you can parametrically suppress any sort of commutation relations between U of G and the operator at X. So for example, this can even be black hole. And as far as you make these regions much smaller than the size of the horizon of the black hole, then the charged black hole operator would commute with this unitary. You had a question.
Yeah, I mean, so you had a bound.
Oh yeah. So let me show you the bound.
No, I mean, okay.
Well, something like that.
I was thinking about the neutrino versus the.
Yeah, so I guess you're referring to this bound.
Yeah, and my question is total ignorance with somebody who comes from a rather different area. Is the dark energy density of the universe time dependent? That is to say, if I go back in time.
Right.
Pardon?
Yes. That's why we don't know.
Because and does that further constrain masses of neutrinos? Unless you want to say that neutrinos also have time-dependent masses, which you probably don't.
Very good question. So we don't know whether lambda is constant or not, and this is something that we are sort of we means collectively we. The astrophysics experimenters are measuring very carefully. So they are measuring what's called the equation of state of dark energy, and So within the error bar that they have measured, it's consistent with lambda being constant, but there are speculations that it's not exactly constant. It might be time varying, but we don't know. Yes. So indeed, you are quite right that if lambda is time dependent, then this inequality is time dependent. Does this go lower or upper? I do not know. I'm only saying that in the current universe, we know that low energy effective theory is described by standard model of particle physics with Einstein gravity, with this cosmological constant, and we assume that that's a mathematically consistent low energy theory, and that's the only input I used. And from that, we can infer this input. Yes, it's a very good question. I have thought about it, but I think I have to think more carefully. Yes, indeed, there is actually another question of the question of whether cosmological constant or dark energy is time dependent or not is closely related to the other conjecture I wanted to discuss, but I didn't have time. So yeah, so that's a very interesting question. Yes, thank you.
Any other questions?
Could you give a 2-minute version of the last one?
The digital conjecture, yes, I can talk about digital conjecture. So this is a this is a following question. So our universe has positive cosmology, positive dark energy. So evidence suggests that well, it is some kind of Casimir energy or ground state energy of our current universe related to the ground state energy of the current universe. But there is a question of whether you can actually realize it as a cosmological constant. So the easiest way the most simple way to actually explain our current universe is that low energy effective theory is Einstein gravity plus Einstein's cosmological term with constant cosmological constant. But in order to reproduce that from string theory or any quantum gravity theory, it has proven to be very hard. And so there is this basic program called Dine-Zyberg program, which is the following question. So if you start with some ultraviolet theory like string theory, there are lots of scalar fields in the theory, and all of them has to become massive, because if you have massless scalar field, then it is inconsistent with what we understand about the evolution of our universe. And so, for example, so therefore, all the field has to become massive. So that means that the potential for scalar field has to have some kind of minimum, and we should be sitting at that minimum. And it's very hard to engineer that to make this minimum to have positive vacuum energy. And so the reason is that, at least to demonstrate that that we have a non-trivial minimum with positive vacuum energy, and this is called Dine-Zyberg problem. And it is related to the fact that the coupling constant in string theory is one of the parameters in the theory, but it's actually given by expectation value of one of the scalar. And so in order to be able to demonstrate the existence of such minimum in sort of perturbative calculation, you have to have we know that in perturbatively we can calculate the potential, and you can show that asymptotically it becomes, the potential goes to 0. So that means that you have to have this kind of bump, and then demonstrated this kind of bump is very hard, and so that was sort of called Dine-Zyberg problem that was pointed out many years ago. And so Qumran Baffa and I was motivated by distance conjecture and Busso's entropy bound to come up with a sort of more quantitative way to formulate distance conjecture, which leads to the inequality or the derivative of the scalar potential. And so this is sort of statement of distance conjecture, that if you have scalar potential, then its derivative can be bounded by this type of inequality. And so this in particular prohibit constant cosmological constant, because if there was a constant cosmological constant, at that point the derivative of the potential has to vanish. But actually, the derivative is bounded below by this inequality. So that's sort of the main idea about distance conjecture. And so this, for example, leads to so this is a paper by my colleague Hiroshi Murayama and collaborators. So this leads to again another constraint on the tensor scalar ratio. So that's sort of brief summary.
Any more questions? Well, if not, let's thank Hiroshi for
Thank you.